All right. So last time we met, we've been talking about polynomials. So just to recap a little bit from last time, let's say that we have the polynomial actually, let's do that. Let's say we have this polynomial. How do we write this polynomial in standard form? What's going to be, how do we write that polynomial in standard form? Which monomial comes first? Good. Negative 7x to the fifth. That's the one with the biggest exponent. Then, what comes next? 18x to the third. And then 5x squared. And then lastly, 6x. Everybody's happy with that? Okay? If I wanted the leading term for that polynomial, what would that be? When we say leading term for the polynomial, what are we talking about there? It's not 18. Negative 7x to the fifth. The leading term is just the first term in the standard form polynomial, or it's the monomial piece with the highest degree. Can we stop talking, please? Thank you. What's the leading coefficient? It is negative 7. That's just the coefficient on the leading term. How many terms does this polynomial have? Hello? Yes, good. So we have 1, 2, 3, 4 polynomials. Or I'm sorry, monomials. Right? 4 terms. What's the degree for this polynomial? What was that? 5 is correct. So remember, the degree of the polynomial is the same as the maximum degree of its monomial pieces. So here the degree is 5. And what's the constant term here? The constant term. What was that? There isn't one, so we'd write 0. Because we could always write plus 0 at the end, right? So the constant term is the term that has no variables on it. Here, all of our terms have variables on it, so there is no constant term. So we can just write it as 1. Okay, that was basically what we did yesterday. Today, we're going to continue talking about polynomials by talking about operations on polynomials. So let's just say we have a couple of example polynomials. Let's say we have our f of x, which is x cubed minus 2x squared plus 3, and a g of x, which is 2x to the fourth minus x cubed plus 2x minus, 4. Okay with that? So, the first operation that we'll talk about is addition. So, let's say I'm interested in the polynomial f plus g of x. How am I going to do that? Well, I'll just do f of x plus g of x. And what does that really boil down to? We're just going to be combining like terms, right? Everybody agree with that? Okay. So, if I want to write my answer in standard form, what's the first monomial I would write? 2x to the fourth. Good. And then what? Are you sure? Minus 2x squared. Good. Why didn't we have any x cubes? Because they added to give us 0, right? They cancel each other out. Very good. Okay, what happens next? Okay, and then minus 1. Everybody happy with that? Not a big deal, right? Pretty easy. Combine some like terms, write in standard form. Those are both easy things to do. What if we asked about subtraction? Well, if I want to find the polynomial f minus g of x, that's the same thing as f of x minus g of x. So it's almost the same thing as before. The only catch is I have to make sure I'm subtracting all of g of x and not just its leading term. So it's very tempting to forget that set of parentheses that I put around g of x and just subtract the 4x to the, or the 2x to the fourth. But I need to make sure that that negative sign distributes to everything in g of x. And now that I've done that distributing of the negative, now I'm ready to just combine like terms in it, just like the problem from before. So if I wanted to write my answer in standard form, what monomial comes first? Negative 2x to the fourth is correct. And then what? 2x cubed, or 2x to the third. Very good. Then? Minus 2x squared. Good. And then? Minus 2x. And last, plus 7. Everybody okay there? Hopefully not a big deal. So if we want to do multiplication, if I do f times g of x, that's the same thing as f of x times g of x. Everybody's okay there? So, f of x is x cubed minus 2x squared plus 3x. And then g of x was 2x to the fourth minus x cubed plus 2x minus 4. How do you think I would multiply those two things together? how would I multiply those two things together? What does this kind of look like? What was that? Kind of looks like foiling, right? So we'd have to do like a little bit of a modified version because we don't have two things on each side. What it basically boils down to is I need to make sure that each term in the first polynomial multiplies each term in the second polynomial. And oy vey, that's a lot of multiplications, right? That's a fine method to do that. Here's the problem though, right? Well, it's not only is it a lot, but it's a lot to keep track of, right? Maybe there's a better way for us to organize this, our work, so that we don't lose track of something. So I'm going to introduce you guys to a method called the grid or the box or the rectangle or whatever you want to call it. And it's really the same thing as foiling. It's just going to be useful for keeping track of all of these little multiplications. And it actually makes life pretty easy, although it takes up kind of a lot of space. So, whatever. So what I'm going to do is I'm going to draw a grid where one polynomial is basically going to be like the width of the grid, and the other polynomial is going to be the height of the grid. So let's use f as the width. So I have x cubed, and then I'll have minus 2x squared, and then I'm going to put a 0x there, and then I'm going to have the plus 3. You'll see why I put that 0x there in a moment. Now I'm going to use the other polynomial for the height. So I have 2x to the fourth minus x to the third. And then, just like before, I'm going to do a 0x squared. Then I'll have my plus 2x, and then a minus 4. Everybody okay with the grid that I've made here? Okay. So each of these boxes in the grid is going to represent a multiplication problem. So this first box is going to be the product of x to the third times 2x to the fourth. When I multiply those two things together, what do I get? Good, 2x to the seventh. So we add the exponents when we multiply. Let's say we move one box over. How would I get this box? Negative 2x squared times 2x to the fourth. So that's negative 4x to the sixth. And I'm going to continue going in the same pattern. Why don't you guys start trying to fill in the rest of your grid, doing the same thing that we've been doing. I'll give you guys a minute or two head start, and then I'll start filling in behind you, and we'll probably meet somewhere close to the end. So, there's the grid filled in. What patterns do you notice there in our answers? Good. The exponent decreases as you go down. If you look at the first column, we have x to the 7th, x to the 6th, x to the 5th, 4th, 3rd. Same thing for the next two columns. What else? What happens as you go from left to right? The exponent also decreases as we go from left to right. If I look at the first row, I go x to the 7th, 6th, 5th, 4th. What if you look along the diagonals? The exponents are the same, right? And that's the feature of this that is really nice, because what's that telling us? Those are our like terms that we need to combine together to get our final answer exactly right. So not only does this grid make sure that we do every multiplication we need to do, because there's a spot for us if we wouldn't leave like a section blank. It's hard to forget to do that if there's a blank for it. And it organizes the like terms for us, so we don't have to hunt through like 12 things to find like, oh, did I get all the x squareds out of there? It's like, oh no, I know I did because I looked along the same diagonal. So let's see, I'd have 2x to the 7th minus 5x to the 6th plus 2x to the 5th plus 8x to the 4th minus 11x to the 3rd plus 8x squared plus 6x minus 12. So the grid just helps us keep everything organized, right? Make sure we do all the little multiplication problems that we need to do. And then it makes it easy for us to find the like terms that need to be combined because they're on the diagonals. So, question now, why did I include those zeros? Right, we had these, I put those extra zeros in there. Why did I include those? Yeah, I had to make sure I included those so everything lined up the way it needs to, right? If I don't include those, there's a step in my row where I go from the 6th to the 4th, and I skip the x to the 5th. So if I lined up my diagonals, they wouldn't line up anymore. So the zeros are important because they make sure everything lines up and keeps nice and organized because it allows us, and then that helps us get the like terms really easily. Andrew? Right. So if you skip the zeros, you have to be super careful now in combining the like terms because the diagonals are no longer going to be like terms. So you can skip the zeros, that's fine. I don't know why you would, because what's the easiest thing to do? The ones with the zeros in it, because you just know it's zeros all the way down, right? Yeah.
If you were to put the zeros in, do you put them always after the second number?
So you want to put them in where they would go in order in standard form. So notice here I have a 4th, a 3rd, and then I have a 1st. So I know I'm missing the x to the 2nd, so that I have to put the 0 in between the x to the 3rd and the x to the 1st.
Okay, so it's to fill in the blank.
Yes, it's to fill in the missing terms in our standard form polynomial. So over here you notice we had x to the 3rd, x to the 2nd, and then a constant. We're missing just the x's, so I know I had to put between the x squared and the constant a 0x. So I'm putting the zeros in where the term is skipped. Does that make sense?
Yeah.
They happen to both be the second thing, but that's coincidence. Poor planning maybe on my part. But that's a good question. Where do you put the zeros? That's an important question. Okay. How do we feel about addition, subtraction, multiplication? Yeah, this is not bad, right? We do have division, which is not easy. But I want to talk a bit more about these two topics first. Okay? What I want to do is I want to look at the degree in relation to these things. So if I look at f, what's the degree for f? Yeah. What's the degree of that polynomial? It is 3, because the biggest exponent is 3. What's the degree for g? 4. Okay, let's go down and look at our answer for f plus g. What's the degree for that? That's also 4. Do you see a relationship between the degree of fg and the degree of f plus g? Well, the degree of g and the degree of f plus g is the same, right? So what is the rule going on here?
The equation with the highest degree is going to have the addition.
Good. Yeah, so we would say the degree of f plus g is the maximum of the degree of f and the degree of g. Now, we've written an equal sign here. Is it always going to be equal?
No.
No. What else could happen? Could it be bigger or could it be smaller? It could be smaller. Let's see an example. So let's say f is x squared plus 1, and g is negative x squared plus x. So here I have a degree 2, and here I have a degree 2. And when I do f plus g, what do I get? Yeah, if I do f plus g, what do I get? I get x plus 1, right? Everybody agree with that? Which is a degree 1, right? So it is possible here for this to not be equal like we've seen. It could be less than or equal to. When is it going to be less than or equal to? When the leading terms cancel out. Yeah. Does everybody kind of see that? So it's not strictly equal to, although most of the time it probably would be, but it could be less, right, if the leading terms cancel. And everybody okay with that idea? So here's your example of the less than, is the stuff in the red there. That's what we were doing. Just demonstrating that it is possible to add f and g and get a degree less than either f or g. Right? And obviously the same thing is true for subtraction, right? Do you suppose you get the less than more often or less often when you subtract? Probably more often, yeah, because you have if you're subtracting, you have the better odds of the leading terms canceling out. Here's a question. So we've seen an example here where we add two polynomials and the degree is less than either of the two polynomials we added together. Is there any condition that would need to be present in order for the less than, the strict less than, to be an option? Actually, let me rephrase to make it a little bit easier. Suppose I have f is a degree 4 polynomial and g is a degree 3 polynomial. Is it possible that when I add them together I get something that I don't get a degree 4 polynomial? Is it possible to get anything other than a degree 4 if I had a degree 4 and a degree 3 together? So not quite. So if I have a degree 4, like x to the 4th plus something, and the degree 3, like x to the 3rd plus something, is it ever possible to add those together and get it something other than an x to the 4th plus stuff? That has to happen, right? Because we add like terms, right? There is no x to the 4th term here to add it with, so I'm always going to get that x to the 4th term coming through. What's the only time when I add two polynomials I could get a degree less than the maximum? When the degrees are equal. Right? If f and g are the same degree, it's possible now the leading terms could cancel each other out. If they're different degrees, you can't cancel the leading terms because the leading terms aren't like terms anymore, right? We'd be trying to cancel an x to the 3rd with an x to the 4th, and those two aren't like terms. You couldn't cancel it. Is that, we see that? Okay. Let's go down and look at the multiplication here. So again, we saw that the degree of f was 3. The degree of g was 4. And what is our degree for f times g that we just wrote there above? Yeah, that's this guy that we wrote just a second ago. Okay, that's a degree 7. You guys see a relationship here between 3, 4, and 7. Yeah, so the degree of f times g is equal to the degree of f plus the degree of g. Is it ever possible that that's not true? Could I get more? No. Could I get less? Maybe. So the only way to get less is a very stupid situation. So let me show you the one time where you could get less. Say x is, or f is x squared plus x plus 1. The only way I could get less is if g is just the 0 polynomial. Because f times g is 0, which is a degree 0. But if we don't count 0 as a polynomial, then we're good. As long as if we throw out the 0 polynomial as something that we count here, or if we just say f and g are non-zero, then it is always true. So for our practical purposes, this is always going to be true. That's the only way it would fail, is if one of the two were 0, which is not super interesting. Because 0 times anything is just 0. So, but we're talking about, right? Like those little counterexamples of like, when might this rule fail are important. Okay. I think that's good for today, guys.